everyone. On behalf of the Indian Institute of Technology Institute Lecture Series Committee, I welcome each one of you to this unique institute lecture, which is 29th in number, being scheduled on 29th of January. So this Manikanchan Sanyog is there, and there was a book of World Watch Institute, which had a title called 29th Day. So if you see the abstract, Professor Seeram says that these nanofibers can be utilized for solving environmental problems also. Abstract is there with each one of you. On behalf of Institute Lecture Series, I again want to inform you that this series has now built up well, is percolating well amongst students, present students, alumni, and I am getting repeated requests from the alumni to get the recordings, video recordings of these lectures available online. So for your information and for informing others, we today have an Institute Lecture Series YouTube channel in which every lecture is broadcasted after the lecture. We are pretty sure that in this digital world, physical presence is becoming less important and online presence is much more important. So we have an Institute Lecture Series Facebook page. We have a YouTube channel. We are also there on Twitter, and we are very soon going to be on LinkedIn. This event is a collaborative effort of the Students' Parliament through all its councils, and the poster that you are seeing, the beautiful 3D poster, has been made by them within a very short period of time of 1 day, and they completed it by burning their midnight oil, and they ended up completing it at 2 o'clock. So they WhatsApped me at 2 o'clock, we went ahead. So the result of that is, with all these efforts are minuscule if we compare that with the efforts taken by the speaker of the day. He has come all the way from National University of Singapore, and we are going to be blessed with his lecture because he is one of the most cited person of the world today. And while I was discussing with him during the lunch, he came to this field by a chance. He was not wanting to come. His dean compelled him because he was a junior faculty member. So I asked him, was it a punishment? He said, almost like that. So I said, the punishment changed your path? He said, yes. But this punishment he converted into an asset, and today he is one of the most cited person on nanofibers. And he is a mechanical engineer by training, but from mechanical he has traversed a path of nanofibers. We'll be listening more in detail. And today, as you see the world, we find more and more applications of nano is going to take place. Equally illustrious is our Dean Academic Affairs, who is going to preside this lecture today. So I'll request Professor Sinha to accompany Professor Seeram, and I'll request both of them to garland our founder on the way.
Thank you, Professor Sharma. Good evening to all of you. I'm finding it very difficult to introduce such a illustrious personality actually. When I saw his biodata, then I thought he must be a very old person. So when I met, then my whole of my conception got changed actually. And he's such a young guy with such a illustrious biodata. It's really remarkable, and I feel very honored in given an opportunity to introduce him. And Professor Sharma has already told that he has a very high citation index of I think greater than 127. So it is almost I think more than or at least same to the Nobel laureate, 2016 chemistry Nobel laureate, Fraser Stewart. So he is such a illustrious person with having more than 1,000 publications and having 72,000 citations. So I was finding it very difficult how to consolidate all his achievements into such a small. Actually, if I want to go through his biodata, I think the whole lecture will be his biodata. So that's why I have very, you can say, very salient features of his biodata I will give you, and then by his talk himself, he will be able to communicate what he is. Dr. Seeram Ramakrishna is a professor of mechanical engineering actually. So he is a background of mechanical engineering, working in different areas, particularly also in biologicals, at the National University of Singapore. And you all know that National University of Singapore is ranked first in Asia, and it is the top 20 universities in the world. So you can imagine the status of the university. And he is a nanotechnology pioneer in Singapore. So he started all the activities in the nano field in the National University of Singapore. And he is a member of World Economic Forum Committee on Future of Production. And he is right coming from there only. He chairs the Future of Manufacturing at the Institution of Engineers Singapore and a member of Smart Manufacturing Technical Committee of Singapore. As I told you, because as academic profiling, that is, his international journal papers are more than 1,000, 72,000 citations, and almost 127 H index. And he is highly cited researcher in material science. Thomson Reuters, as per the Thomson Reuters, identified him among the world's most influential scientific minds. A European study placed him at 3 among the only 6 researchers from the Singapore with H index over 100. And he has 1,600 highly cited researchers who are in the world. So he is among that in the world. He received PhD from the University of Cambridge, UK, and the General Management training from the Harvard University, USA. He received numerous recognitions which include International Federation of Engineers Educator Society President Award, Global Visionary, GDC Ambassador, Asian Outstanding Engineer Awards. That is very important. And then IPS Prestigious Engineering Achievement Award, NUS Outstanding Research Award, CPS Biomaterial Award, Cambridge Nehru Fellowship, and LKY Fellowship, Singapore. So many others are also there, but we have just compiled some of them. I am just listing some of them. He is an elected International Fellow of Royal Academy of Engineering, UK, Academy of Engineering, Singapore, National Academy of Engineering, India. So he has roots in India as well. I was talking to him yesterday and he was telling all about the AICT chairman and many other persons like Kakutkar and other people fellow who was quite associated with him in many projects. Then he is also the Asian Academy of Engineering and Technology, Institution of Engineers Singapore, American Association of Advancement of Science, then American Society for Mechanical Engineers, American Institute of Medical and Biological Engineering. So engineer, mechanical engineering also associated with the medical and bioengineering. That's a very important amalgamation between the engineering and the biology. And his academic leadership includes his being the University Vice President, particularly research, as a research director, and Dean of Faculty Engineering, Director of National University of Singapore Enterprise, Director of National University of Singapore Industry Liaison Officer, Founding Director of NUS Bioengineering, Founding Co-Director of NUS Nanoscience Nanotechnology Initiative. As a founding chairman, he championed the establishment with almost 120 million. So you can imagine, 120 million solar energy under his watch as a Dean of Engineering. So he has so much of funds. He mentored the Nuclear Science and Engineering Research Education Study Group. He served as a board member of several national organizations, policy institutes, and tertiary educational institutions. He co-founded the Global Engineering Dean Council while serving as a vice president of International Federation of Engineering Educator Society. He authored the book, The Changing Face of Innovation. So he has a lot many things in literary also. He advises international organizations, governments, corporations, and university around the world. And this is a very, I have concised a lot so that you can have a glimpse of the personality that is before us. So I think, not going beyond that, I will just invite, this time is running out, so I will invite you to start with your speech here, Professor Seeram. Thank you.
Thank you, Professor Sanjay Singh, for the kind and warm introduction, as well as a great host for me for my visit to this institute. I also would like to thank Professor S.K. Sharma for beginning the whole meeting, lecture series, introducing about the Institute lecture series. Also, I'd like to thank Professor Sinha, who is actually chairing my lecture, deans, senior faculty members, students, other interested community of this institute lecture. A very good afternoon to you. Good afternoon. Good. Okay, what do you see there? Me? Does it look like me? Okay. But I noticed those students who burned the midnight oil, they chose to take a photo of me on the website, which is that one. That was taken a few years ago. When I saw the poster, I was imagining what was I doing at that time. Right? And it came to my mind, it was very clear. I was giving a talk about, it's the 147th birth anniversary of Mahatma Gandhi. So I was asked to give a speech, what your concept, your views about Mahatma Gandhi. You know I'm a mechanical engineer, you know I'm a material scientist, right? What can a material scientist talk about Mahatma Gandhi? I'm not a humanities person, not a political scientist. But it was good. I took the opportunity. I focused, that was 3 years ago, I focused on what is Gandhi's mind. And in that process, I learned a little bit about mind. And that smile out there, it was because I really felt I understood something about the mind. Not Gandhi's mind, my own mind. And I'm here is a place, really the spiritual place of India. In fact, the flight I took, the Vistara, the pilot, before it landed in Varanasi, he made an announcement. He said, "Ladies and gentlemen, we are about to land in the most spiritual place of India. You're welcome." So I really got home the message. And last 24 hours I was here. I've been focusing on what can I learn about mind. I know some of you are getting worried. Is he going to talk about nanofibers or the mind? I will come to nanofibers and the mind. I will bring them together. So that was actually the picture when I was thinking about the mind, and that's a real coincidence I'm here at this particular institute. As I was walking through your departments, I looked at the architecture. It almost felt I was either at Harvard or MIT the architecture was very similar. High ceilings, beautiful walkways. So really fantastic place, and I'm glad to be here with you, and thank you for having me here. I appreciate that. So I'm not going to go through that, but basically I'm trying to say that was when I was talking about the Gandhi's mind, then it's my own mind, that's how I look like. That's a normal mind. Okay, so as I said, it was fantastic for me to a place where I had a glimpse of what the human mind can, the diversity of thinking, and a broadness and depth and richness of the human mind. So I will bring this nanofibers connection to that in a while. And you could see the proof that I've been going around busy. Instead of sleeping, I was just going around and absorbing as much as I can from this place. So if you notice here, it just came out probably 3-4 days ago in the international news, also covered in India. So they discovered a fossil which talks about the humans being around for 200,000 years. 200,000 years. We're not talking about 5,000. We're not talking about 10,000. Not 50,000. 200,000 years ago. So that's the human migration. So fundamentally, the human society, we could capture the progress in those, what they call Society 1.0, which is hunter-gatherer, Society 2.0, agriculture, Society 3.0, industrial revolution, and Society 4.0, information revolution. So clearly, India had participated very well in Society 2.0, as well as 4.0. I'm very sure the next one, now already people are envisioning what they call Society 5.0. In this case, it's a seamless merging of physical space and a cyberspace. And you can imagine a society that harnesses, that advances in a physical space as well as cyberspace, eventually meeting the needs of the human beings. Yeah? So that's the future. I'm coming to how is this material guy involved in these things? I'm coming to that. So if you notice, it basically talks about emerging technologies like artificial intelligence, machine learning, big data, and augmented reality. These are the new buzzwords. Also, a lot of investments are happening in this area. So these guys, when they were going around, fundamentally they are in search of the same thing, which is the human needs, quality living, health, security, and sustainability. We all need education as well as some level of understanding about spirituality, no matter where we are. So what I believe is, while human needs remain the same throughout the 200,000 years, there are new opportunities that are emerging. The first one right up there is the mind. So I actually believe the mind-inspired technologies, we're yet to see them, and they're going to come. This is where the role for material scientists as well as the rest of it. So that's why I strongly believe that's a new frontier. You would also see deep ocean technologies coming up. Right now you can only go up to 5,000 probably meters. But there would be technologies now very soon, 10,000, 15,000 meters. Similarly, subterranean technologies, probably 1,000 meters right now. You could imagine in the future going down to 5,000, maybe 7,000 meters below the ground. And then space technologies, which we talked about. So these are the things which I believe might be emerging. Okay, here is the eye test. The one sitting at the back, can you read it? I know you can't. So don't worry, because that's the best I could do, because about 3 months ago, I was asked by about 200 deans, rectors, presidents of US and Canadian universities, Seeram, can you come and tell us how the world will be in 2050 and 2100. And they also asked me, can you come up with what could be the future jobs, not the present jobs? What kind of jobs that might be there? So what you have is on left side, what kind of new engineering jobs in 2050? On the other side, 2100, what kind of new engineering jobs? So while I was doing that, I was only thinking only one thing. I can predict and say whatever I want, because 2100 I won't be around, right? So it's up to you to deny he didn't get it right. That's fine, but I thought it's good to give a best shot and explain it, and it was very well received. And I believe many of those things, an institution like IIT BHU, as you are putting many centers together, as you're ramping up your R&D activities and training activities, I'm sure some of that would be part of your future directions. So that's what I felt. So now, I'm always tempted to talk about things I don't know. So here is one of those things which I don't know actually. So what I believe, there are 5 fundamental perennial questions, and it's probably the place to place it here because it's Benares, Kashi. Origin of life, nature of life, what is consciousness, what transcends death, why everything exists. I just don't get, there are lots of versions out there, but I'm still trying to understand more deeply. And some are already convinced, but many others around the world, they're still probing. So as a scientist, I thought the basic disciplines would be probably some of those would help us to fathom them. And engineering means all aspects of engineering. Then I chose one of the core area, which is basically the stem cells, quantum energy. You could dispute with me, the future could be different. Neural interfaces, nanotechnology, and AI. So what I'm going to tell you is how we are playing a role in this area, neural interfaces and nanotechnology through nanofibers. So I will show you with examples. And we also do some work on stem cells. So it's an interdisciplinary work. And so what drives me to do research is not these, actually these. And that's fascinating to learn as much as we can because human knowledge is very broad and wide and deep. So that's pretty much what I think are the perennial questions we still need to understand. So you as a future scientists and scholars, probably you would be able to break through, come up with a new understanding. Okay, let's get to nanofibers, otherwise you are getting a bit worried. This guy is some philosophy, or lost in thinking, talking something else. Let's get to the fibers, and I'll connect back to all these things. Okay, what do you see there? Cotton candy. How many of you did not try cotton candy? Did not try. Clear. Everyone tasted it. Cotton candy is made of sugar. Why does it taste better than sugar? It's because you made that into fiber, and that fiber is very thin, and when you put it on your tongue, it feels good. More than that, what they do is they heat the sugar, almost molten stage, and they're spinning. When it is coming out, the fibers gets formed, and it gets cooled very fast. There is probably change in a little bit of microstructure, and that's why it tastes slightly better. Of course, there are colors added to them, and this is a happy feeling, so you would like it much more because in the mind that you are taking it. So pretty much all my research is all about that, cotton candy. I use that technique and then develop the whole range of applications for nanofibers. So I will show you those things. But the concept is exactly that. So if you want to understand exactly how the nanofibers are made, I have slides which shows exactly how the fibers are formed and how we actually control them. And a lot of tricks are there. Those slides are there at the end of my presentation. I was told better you give a talk about 30 minutes and then we have at least 20 minutes or 25 minutes for Q&A. So I do think it's a good format. So I will try to limit my total presentation to maybe 30 or 35 minutes. You have more chance to ask me the questions. At that time, if you need to see the technical details, I'll show you actually how it is done, if you are not familiar with the concept. So the reason it got more popular was I came up with the first book on electrospinning and nanofibers in 2005. It basically opened up opportunities for scores of researchers around the world just learn it themselves, practice it by themselves. So that was the intention. There is a story behind it, why I wrote that one, but that's essentially a very popular book. And recently we wrote another one on Cambridge University Press. This came out on the left side. So if you look at the number of publications in the area, right now about 2,000 plus papers get published. And you see the three significant points where I entered into this field in about 2000. Our publication came in 2003. Literally the field caught up across the world. And that was a happy story. So you enter into a research domain, when it is picking up, hopefully it goes up, and you also have the benefit of the field as it develops. But the point here is, look at the number of papers. It's about 2,500. Look at this one. Number of papers that are getting published every year across the world is close to 2.5 million journal papers. 2.5 million journal papers a year. There are more than 10,000 journals. So now you are a researcher. How on the earth you're going to read all those papers to write your introduction section? Of course, you have to do it faster and more effective. Right? I know some of you know that's a huge number of these. About 2,000 is not that many papers, but last 17 years is a huge. Yeah. So what you see is that kind of trend. So this is where a new field which we just started called materials informatics. You see there, it's got published there. So what we are saying is we will use techniques like machine learning, AI and data analytics. We read the papers automatically. And a computer organizes the information I want. It extracts information from the published papers. So I can read 2,000 papers. I don't read it. My computer reads it, and it gives me the data. Right? So now what am I doing? I'm actually applying this to my own field, which is electrospinning. And I'll show you. I have a few PhD students working on this. So it has lots of components. You could do the modeling, you could do the other things, and then there's other things you can integrate. Yeah, this is what we call materials informatics. And what it can deliver is a web-based informatics program where you could use it to select the materials and improve the functional performance, simulate. Also, you can design materials with the better environmental performance. That means you can mine all the information, and in the future, when you are designing a product, you make it much more environmentally friendly. I'll give an example. Most of you have a smartphone. All the smartphones, when they actually market, they announce what is the carbon footprint of that product. Apple does it, Samsung does it. So most of these products, they claim they're environmentally friendly, and they have to declare that. So how you make the next version much more environmentally friendly is you do the material selection, which are designed for much more eco-friendly. So these materials informatics tools are helpful. Yeah. So you'll be wondering, if that's all my solution is, you don't need a materials informatics, right? You remember that one? Yeah? Yeah? I had this morning, yeah. So I took the photo. You can see fresh. I went there. So as an evidence that I'm serious about learning about the mind. And then I realized, actually, you are already doing the environmentally friendly way. You don't need those plastic cups or all those cups. So some things are there in the culture, and sometimes it's not there in the culture. Then you need these kind of tools to mine the information from the websites as well as published papers, come up with an alternative materials. Now that's materials informatics. So here is an example, a drug delivery, where we look all the papers published in drug delivery, and then we link to the nanotechnology or nanofibers, and then I can pick up automatically. Basically, computer does it. So I'm applying AI to the materials world. So materials world is now changing to a different domain. I just want to say, and I have slides to go through how actually we do that. Yeah? So if time is there, I will get there. So what you see here, these are electrospinning machines. We design and build them. Here, this is your writing pen. This is the smallest electrospinning machine that is ever built. Yeah. So we actually design and build a machine. You can see it. And it operates on a pen cell battery. But you can also do a bigger scale, lab scale. This is industrial scale. This width we are talking about 1.5 meters wide and several thousands of meters long. So it's a scalable commercial type of technology. So I'm not talking about a technology which is based just for labs. This is actually a scalable technology. So we have done all this from smallest machine to the biggest machine. We design and build them. So that's part of that. And we looked at the markets, air filtration. Say in this place, in a different kind of buildings, you would see the air filters would have these nanofibers. Liquid filtration, which means basically water filtration, as well as in biological, in biotechnology, you need a lot of filters, and textiles, and food, and composites. So these are the large volume areas where we developed some work. Here is an example. This is our product. This is basically industrial air filters to filter the air. So you have a commercial manufacturing plant, or you have agricultural tractors. They need that kind of filters so that air is filtered before it gets to the inner compartments. So that's a commercial product. You also see the windscreens, which has this nanofiber on it. So it filters. At the same time, the air comes in. If you shut the window, no air is coming. So you have to use the aircon, the overload on the electricity. Here, it's basically, you have the window frame on which you have the nanofibers. It removes the finer particles. So it makes the living environment better. It's a commercial product. It's our product, yeah. And then I work with this company. We are looking at futuristic jackets. For example, you are going for climbing on Mount Everest. The question is, can you have garments which protects you from cold, at the same time it allows for breathing, better air permeability. So you introduce a layer of nanofibers in these textiles, and this is what we call high performance fabrics. So that's the product. And you also see these are the surgical clots. So let's say there is an accident, there's a bleeding going on, how do you stop it? And here is an emergency case, surgery clot, and that's meant for the bleeding, to manage the bleed. This is a commercial product already. I read yesterday, I think, Tata, former Tata chairman Ratan Tata, also invested in a similar company in India. They're doing something similar. So this is an interesting area in India too. So just to get you into now, all the work I have ever done in the last 17 years is this one. We worked on filtration, separation, textiles, medical and healthcare, composites, nanomaterials, energy and food and nutrition. We're looking at air filtration, liquid, gas separators, textiles, basically high performance textiles, medical textiles, stem cells, biomaterials, regenerative medicine, tissue engineering. And then we get to the composites, nanomaterials, energy, basically solar cells, batteries, and then food packaging and nutrition delivery, supplements. So this basically covers a simple cotton candy technique. We just imagine what is possible. We just tried it. Same approach, no change. The fundamental technology is same. We just adopted it for a different scenarios. So you could see them. So we now go into one specific example, which is more in line with the current trend, and I'll give you several examples so that you are convinced there is some interesting work can be done using this nanotechnology. Okay, what do you see there? Yeah, it's me, right? Yeah. So you could see it's a different avatar. Basically, I'm a journalist there. So I also write articles for the newspapers, popularizing the science. In Singapore, we do that. So I wrote about the in search of a smart shirt. What that means is a shirt or a garment, when you wear it, you just feel like in the morning, well, I'm going to the office. So you want a more formal colors. But in the evening, you want to go for a party. You don't have time to go home. But you want the garment to change the color. Is that possible? Why not? So, you can imagine that. Let's say I'm feeling not so good, lonely. All I need is a hug, right? In fact, a hug does a lot of help. If you don't believe me, go and read all the neuroscientist guys. A physical touch, just touch, somebody puts a hand around you, you just feel good. So imagine a garment, it senses your mood, and it gives you a little bit of tight fit. You already feel patted, right? And there's lots of lonely people in the world. If you don't believe me, UK just announced a new minister for loneliness. Yeah, exactly. Can you imagine? UK, you have a minister for loneliness. That's life. That's how things are changing. So anyway, but in our case, we're not only talking about loneliness, we're talking about how do you introduce power generation systems? How do you generate conductive wires? How do you talk about communication from your garments? So what we call different aspects, how we can build them into the fiber structures. So here is an example, what we call piezoelectric materials. So these are the materials when you apply a mechanical force basically produce electricity, and converse is true. So these are the standard piezoelectric materials. Those in ceramics, they would know, piezo-T. But a known one in polymers is PVDF, polyvinyl chloride. So we take the PVDF, which is a polymer, we can spin into a fabric. And that's a PVDF structure. We won't go into the details. And these are mechanisms. I won't go into those details. Now I'm going to go faster so that I'll just show you the results. So what you see here is that D33 is a piezoelectric constant. This is the material which we made PVDF. It's the highest reported in the literature. So that can be converted. These are mechanisms. We converted a specific application. For example, there are aging people. Parkinson's disease is common, or at least more people would have it. Parkinson's disease means you have a tremors. Yeah? So it's a big problem. If you have to do work, which precision work, you have a tremors, you won't be able to do it. So you need to go for medication. So the doctor need to know your tremor profiles. So here is a device that is built using this PVDF nanofibers. It's like a ring, and these are just the details. So we put these fibers cantilever way, we design that, and we measure the signals, the tremors, and that can be sent as a Wi-Fi or through remotely from your mobile phone to the doctor or your family members. Then the doctor basically, let's see. what he does is he look at the information, then he actually tells you how much medicine you should take, because they need to meter the medicine for the Parkinson disease. So a simple nanofiber technology, we adopted for a particular healthcare problem. You could see it. Yeah? So now I take it further. Generating electricity. Imagine a socks. You can wear it around your elbow. So here is an elbow, and this is how we construct this fabric. These are the details. So when you bend, the dielectric poles in the PVDF changes. When you impact, you release, you heat it, cool it. So it is pyroelectric as well as piezoelectric. And I could pick up the signals for different cases from your movements. So here are the details, and you can put that in a shoe. And now the question is, let's say you're doing mountaineering or you're in a remote place. You don't have battery chargers. All you need is a scenario like that where you could charge your battery, mobile phone. So it generates as you walk, and that produces energy, and you store it. So that's the thing we are building now. And these are the details more. So what we do is we actually weave them into the fabric, textile. So you see the fabric is woven, and then these fibers, we actually align them so we get a best property, and then we can actually pick up the signals as this person, the whoever is wearing, as the person is moving, that a mechanical movement is translated into electricity based on the textile, where I have these PVDF nanofibers inserted in the normal textile. Okay. So that's done. So we move on to the next one is, how do I now conduct electricity with a lesser weight material? So normally copper is a standard conductive material, and then there's new material called carbon nanotube. You can't see it, it's so small because the thickness is about 1 to 5 nanometers, so thin the eye cannot see. That's a carbon nanotube. So we take that carbon nanotube, which has a much better electrical thermal properties compared to copper. Copper is the glue, and CNT, carbon nanotube, we integrate them, and then we make those, let me show you. We make this CNT copper, and this is the material we made, and that conducts electricity. So now I can spin that into fibers, and I can weave that into the garments. So now I have energy generation, I have energy tapping or device to transfer the energy, electricity. So now two things are integrated. Now I need to do, the other one is storing the electricity. So just to get you the idea, I don't know anybody working on batteries here, but this guy, John Goodenough, he actually invented lithium-ion battery, the one all your mobile phones have. All your mobile phones have that battery, same battery. Very interesting. The guy invented this battery at the age of 57. And he recently filed another patent at the age of 94. And this is the world average. What's the period you are most prolific in patenting? Between 40 to 60. So what's the message here? If you're planning to retire early, forget about it. Right? You got plenty of time. That's what it is. So you can invent all the time. So anyway, it's just what it is. It's interesting. So we work on lithium-ion batteries, lithium-sulfur, lithium-air batteries. This is the energy density. So this is how we spin the fibers. I will go faster so that we don't spend too much time. So we basically make that into the coin cells. We look at the specific energy capacity and stability with over the number of cycles. So we prove that. And these are more details. And in this case, we use a different polymer system called HCP. Based on the proportion, I can make the light emitting property. So it could have the garment, same material, the way I do it, it could be blue, white, or red colors. So the polymer I play with and I spin it, I get a different colors. So now you can see whatever I said about the smart garments, we're working on a pieces of how to get there. We're building the blocks. Okay? So here is another example. Imagine you have a mask, the one you wear. That mask, you can integrate these fibers and then it can find out, are you happy? Are you normal? Are you sad? Are you sleeping? Especially when I'm giving the talk. All I need to do is give you the mask. It tells me you are not listening to me. I'm joking, but I think we get there. All right? So here is the patterns. We can pick it up because these fibers are embedded in those masks. So how do we do that? Is basically we play with the silver nanoparticles. We embed them into the fibers. The spacing between the nanoparticles is what helps me to manage the process. So the ion conductivity between the nanoparticles that are decorated on the fibers, I could, for different humidity conditions, I get the different signals. So those are related to your moods of you. Yeah, your moods. So this is basically how we actually do that and demonstrate it. This is how a nanofiber decorated with the silver nanoparticles, they look like. So here is an example. Those are integrated into a shirt. And you say nano, you get that pattern. You say perfect, you get a different pattern. It's on your chest. So it's basically a pressure sensor. So we are building several functions into the fiber geometry by varying the materials. But the same electrospinning technique, same cotton candy technique, no different. So if you are, this is a nitrous oxide gas sensor built. If you are still not convinced, here it is. So I know you have India's first ceramics department. This is electrospun ceramic nanofibers. Look at that. How many materials have been electrospun? Yeah, plenty. So people around the world, they spin all kinds of metal oxides and ceramics. Just ceramics. So then you talk about polymers, even more wider range. So that's the flexibility. So I'm going to now switch from the garment to the medical application. I did a lot of work in this area for at least 15 years. And we looked at a number of applications like wound dressing to cardiac patch, a number of them. And some of them are actually companies. So here, for example, you can use that small electrospinner. If there is a wound, you spin those fibers and then you actually do the wound healing. So let's say there's a burn and you could do the wound dressing using this process. So you could see this is our material system. This is the wound. After, say, a certain period, maybe 10 days or 2 weeks, you see the healing. This is on the animal models. This is for the pig models. We've done that. Now it's going for the human trials. Very soon we will do the human trials for the skin problems. Then I go to the nervous system. That's the brain and spinal cord, what we call central nervous system. That's the peripheral nervous system. And that's typically is the axon which is conducting the signals, either motor function or reflection functions, sensory functions. That's how a typical neuron looks like. And you have this polarity across the membrane. And basically this is how a neural signal moves from one end to the other end in a typical neuron. Yeah? So this is how the neurons basically there. You have billions of neurons in your body. Billions. Even your brain itself, the brain itself has at least 100 billion neurons. So the rest of the body will be even more. And those are the guys helping you to sense and as well as move. The point I want to bring is back to the brain and mind. So that's the brain. Last 30 years, this guy called Alain Baird, is a French scientist, a neurosurgeon. He figured out different parts of the brain if you put these electrodes, you can treat certain mental related problems or mind related problems. In this case, a Parkinson disease, someone has a tremors, they would put an electrode and it is connected to a battery which is implanted in you. It sends the signals. And then your Parkinson disease is under control. And I met him, you see this head? That's actually his head. That's the guy. This is the guy, same guy who invented it. Yeah. So I had a chat with him. I asked him, can you tell me where is your mind? He said, I also don't know. Really? He said, brain, no problem, I can explain it. The mind. He's a top neurosurgeon. Then it comes to mind, it's tough. Brain, he could explain it. He's treating it. And he even told me, if you had a bad dream, you woke up, you had a bad dream, and he can put an electrode, and you feel after that, you had a good dream. Yeah. Let's say you are a pessimist, born pessimist. He said, I put an electrode, put a voltage, you feel very optimistic. Yeah, isn't it good? So the question now is, if he can do that kind of things, he said that, by the way, I'm not saying by myself, he told me that. Then the question is, what else is actually the mind? He is able to do those kind of things. So we had to find out what exactly mind we are talking about, much more than that. So I'll just finish on the mind technologies, then I'll say. So basically there's a lot of mind-related technologies coming up. Basically they're integrating to the brain, and then they can now run certain peripheral devices. And now they're going towards implantable electrodes, and then they could tap the signals. So our role, our nanofibers, we are looking at these implantable electrodes, and we are looking at these interfaces, what we call neurointerfaces. And I have 3 PhD students in this area. So what we are doing is we modify the interface so that a few number of neurons are coaxed to go in a particular direction, then we can tap the signals from them. That's what we do. So here is an example how we manage the impedance by controlling the neural interface. It's a normal one, we reduce it by 20 times. We reduce the impedance so we can actually enhance the signal. Otherwise, signal is weak. So now if you want to read real high-level signals from your brain and a very few neurons rather than the whole number of neurons, you got to go in that direction. So this is where nanotechnology, this is where nanofibers come in. That's what my connection is. While I'm doing that, I had this same thing on my back of my mind. The question is, mind arises from the existence of various mental functions. Scientists are gaining mechanistic understanding of the mind, and mind functions are a product of firing circuits of neurons interacting with hormones, enzymes, and body systems. That's what the science says, right? But when I go to spiritual gurus and philosophers, they have a different view. So hopefully, my feeling is I'll put some electrodes in you and me, and I'll figure out your thought and my thought, right? So that you don't need to tell me, sir, your lecture is fantastic or boring. I know what you're thinking, right? Okay, that's my idea. So I don't know how far we got there. It doesn't matter. The future scientists will do. What I did was, as I got so curious, I actually went to the Oxford Dictionary. Not that I'm a fan of English, but that's because I'm an international speaker, I got to use English, so it's easier. To my horror, there are more than 150 descriptors of mind functions. More than 150 descriptors of mind functions, words, in the Oxford Dictionary. Amazing, right? It's confusing too. Right, then it's horrible. If you say something, I don't know what you're saying because I'm using a different word to express what I'm thinking or what I'm feeling. So this is where the communication problem is enormously big, challenging. And of course, they are now relating some of these to the certain regions of the brain and they're getting to the particular neural circuits. And this is where they're applying artificial intelligence as well. And deep learning, they are figuring out. This is where I'm bullish about the mind-inspired technologies, because we may not be able to reproduce all of them, but I'm sure some of those things can be measured, quantified, reproduced, definitely. So the question is, we may not be able to do everything, but some of them will be done in the years ahead. So my summary is, since I'm talking about the mind, basically you can take all these 150 or 140 or 120, doesn't matter. They are basically related to thinking, wanting, desires, and a feeling, senses. Basically you can group them, and then you have this undefined part, which is where the spirituality and concepts come. They use the words consciousness, atma, soul, self, spirit. There's a lot of them. And my belief, everyone else's belief, your health, state of health, education, culture, and experiences, in a way, modifies all these things. And that differentiates each one of us. So this is where the science is coming, is basically now systematically linking these guys with these guys. So that's where the top brain research is happening, mind-related research, cognitive research in the world, absolutely. So I think if you are interested in these kind of directions, it's happening. Anyway, so why I'm here is I took the opportunity to figure out what exactly all this means, and I'm still figuring it out. Yeah. So what we do, we now use the same nanofibers. Now I'm going to the spinal cord injury. Here, this is a human being, squatted. Normally the sports-related injuries or accidents, the spinal cord, it gets affected. So right now we are looking at injecting stem cells into that one to treat them. So you could see here how the stem cells are injected. And we are looking at a macrophage, which is here. Macrophage 2 is for regeneration of the damaged spinal cord, whereas inflammation is mitigated by the macrophage 1. This is a serious problem. There is no real medical solutions right now. Anything related to the spine-related disorders, there's really no medical solution. And so there's a lot of intense research is going on. We have several teams in China where I guide them. We're working on that. So we look at how we use nanofibers to change the lineage of these macrophages from that shape to that shape by changing the fibers, which are basically made by cotton candy concept. So we do that. So these are the examples of how we do the anatomy. Let's see. What do you see there? Yeah, back to brain. It's actually the brain. These are the eyes. That's nose. This guy has basically the brain tumor, what we call glioblastoma. So this is a tumor, and when you excise it, it'll come back again. So people with the brain tumors, right now they are given a period of anywhere between 5 years to 10 years. And there's no cure. That's it. So this is where there's a group in North Carolina, our group, we're looking at applying nanofibers. They release the drug. So we basically put these nanofibers, and then we are looking at the slow release of the drugs that is available. So that skull is open, we put it inside and then do that. And then we are looking at how do we do the shape smart system so that I can control externally by heating in the localized region. So we actually do that. Okay, I go faster now because there's a lot of details. Are you hungry? You are hungry? Okay. But the organizer said there's no dinner. At least I think so. So anyway, back to me. That's not that important. But that's about the high-tech vegan meat. So same tissue engineering principles which I described now being applied to make vegetarian meat. It's actually meat. It's a meat. So, but no cow, no animal is killed. No chicken is killed. So you actually grow the patty. It tastes like the meat. It bleeds like meat, but it is not a meat. Yeah. So if you don't believe me, go to California. You can pay $30. You can have the burger. It's in the restaurants. You can buy it. So happily, this is a Singapore-based company. We invested in this one. But a lot of these technologies are based on these similar things I spoke. So it's very interesting how you can have better alternative systems when you are concerned about animal transmitted diseases or the quality control on the actual rearing of the animals. You probably sidestep the problem. Maybe you create a new problem, but fundamentally technology helps you to come with a new solution. Okay, this I think is a bit too much. This is the antibacterial one. I know our Sharmaji, he wants to know about, is there a use in his area? Here it is. So basically what we call self-healing composites. These are the nanofibers and composite materials. We introduce cross-linkers. So when a material breaks, that cross-linkers come out and then they close the crack. So this is how we introduce. In Italy, this is a product in helmets. So this is how after the break, the properties go down. But once this nanofibers come into picture, self-healing action, you regain the mechanical properties of the material. Okay, I think there's been too much detail. So we are looking at oil and gas sector also. So fundamentally, these are the areas. There's a large volume markets we addressed, but the new areas we're constantly looking at. These are the details of materials informatics. I said I won't go into the details. How we build a system. Okay. Yeah. So this is my last slide. Since the whole title of my presentation is functional fibers, I thought I'll have a slide on this one. My student designed that fabric, and she says, simply me, of course, she says. So I think the garments which we are wearing is going through revolution. It's a standard garments apparels now gone to technical textiles. In the future, you will have wearables which are basically digitally connected to the internet. So that's a possibility. So the research that's being put together is a small contribution in this direction of smart wearables, functional fibers. Well, with that, I just want to say thank you.
So you asked about hydrogen storage in nanofibers. I had worked on that area. We did hydrogen storage in carbon nanofibers, and the results were unexpected. There is a high percentage of storage, and doing lot of characterization, we can find out the reason why there is such high storage, more than metal hydride. So we are continue working on that hydrogen storage. We can talk to you later. I have few quick comments. I am not qualified to comment on your lecture because one thing is that all of you, we understand that nanofiber, nanotechnology, nanoscience has made significant progress in preparation, characterization, functionality itself, and commercialization is now the key issue. And we hope that in years to come, we will see large scale application of these technologies for the benefit of mankind, for the human society. And since I am working as a Dean of Academic Affairs, the second point is for the students. Nanoscience or nanotechnology is not a new science. It is only a complex platform of chemistry, physics, biology, information technology, etc. So it is basically an interdisciplinary research, And nowadays we find that all the cutting edge research or major innovations are at the interface of two or more disciplines. So I will encourage the students to work in the interdisciplinary area. There are many. One example is, of course, the nanotechnology, nanofibers, etc. There are other technologies also. So during your exploratory project or UG project or stream project, your course structure encourages interdisciplinary work. So take advantage and do interdisciplinary research. And the third thing which I want to highlight, that in our institute also there are many faculty working on the area of nanofibers, and some typical things which came to my mind is controlled drug delivery. Professor Misra is there. Then tissue engineering, water purification. We have commercialized a water purification system also. Then photocatalysis for removal of pollutants using. Then development of carbon nanofibers for radiation shielding. And then in the area of fuel cell, solar cell, supercapacitors. So these are few. I might have missed a few also, but quickly I could write these areas where we are working, and through you we will be looking forward to the collaboration between your institute and our institute. I hope you will look forward to you for the further collaboration. Thank you very much.
One minute. I'll take one more minute of yours. I know he talked exceptionally well, and he talked on mind on a mind-boggling way. And since I think 1 o'clock I am with him, every time when he comes out with a narrative, it's a totally different out-of-world experience. So for me, it was an excellent experience. This whole day was made by him. I thank you personally for it. And on behalf of the Institute, I thank you for taking your time out and be with us. And actually, the motto of the Institute lecture was this: educate to innovate and innovate to change. And his lecture has proved that we can innovate for change, that also. And at a very functional level, he has made his topic functional nanofibers. So nanofibers were very functionally explained. This lecture will be available on YouTube, and if Professor permits, we'll take this lecture and share with people who want to build on his lecture. On behalf of the Institute, I thank Professor Sinha also, that who has, in spite of his busy schedule, at a very short notice, he came from outstation today itself, has agreed to preside. And I thank my senior colleagues whose presence give me motivation to go for next institute lecture. And particularly thankful to Sai Teja and team ILS and the students who have made it. In spite of their classes, they are here. And for you people, we have high tea waiting outside so that you can, जो चाय लिमड़ी का नहीं मिला होगा वो यहाँ ले सकते हो. And those of you who have missed the queries, Professor Seeram will be there in high tea with us. You can ask him. Though when you ask him, there is nothing which he will not reply. Now I invite all of you on behalf of the series for a cup of tea with Professor. Sir.